Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at maps. So in mathematics, a map is basically a way of going from an element in one set to an element in another. So each of these diagrams you see here is a map between two sets. I call D the domain and C the codomain. The domain is basically the set where the map starts and the codomain is the set where it ends up. Sometimes these are the same sets. You can have a map from a set to itself. So we're just going to look at these four definitions. So firstly, we're looking at what it means for a map to be a function. So just to add a little bit of ambiguity, some textbooks only class a map as a function. Some would say if it's not a function, it's not a map. Some textbooks don't say that. So a function is just a map where an element from the domain is never mapped to more than one element from the codomain. So this here would be a function because each element in the domain is not paired with more than one element in the codomain. We don't have a situation where one of these elements is mapped to multiple elements. So this here would be a function. This, on the other hand, is not a function because A is mapped to two different elements. Note that all we need is one counterexample, one case where this rule doesn't hold and it's not a function. So I included this map here because, again, there's a bit of ambiguity. Some textbooks say that for a map to be a function, each of these elements in the domain must be mapped. So some books would say this is not a function because C is not mapped. Some textbooks would say it still is a function. So that's only a small point, but I just wanted to make you aware of it. I honestly don't mind whether you consider this a function or not. So a map is said to be injective or one-to-one if each element in the codomain is paired with no more than one element from the domain. So this map here is injective or one-to-one. So the reason it's one-to-one is because each element in the codomain is not paired with more than one element. We don't have a situation where an element here is coming from two different elements. So this here is injective. This map here is not injective. The reason is because D is mapped to by two different elements in the domain. So that's why it's not injective. A map is called surjective or onto if every element from the codomain is paired. So this map here is surjective. It's definitely not injective or one-to-one, but it's surjective because each element here in the second set, the codomain, is actually paired. Even though E is paired with multiple elements, it's still paired, still has a friend there. So too, F has a friend, it is paired. So this map here is surjective. This map here is not surjective or onto because here E is not paired. We have an element in the second set, in the codomain, that is not mapped to. It's not paired. So that is not surjective. So bijective means that the map is both injective and surjective. Of course, those definitions we just went through. So this map here is bijective. So bijective basically means there's a perfect correspondence between elements in D, the domain, and elements in the codomain. You can see each element in the domain is mapped to one and only one element in the codomain. Bijective functions are nice to work with because if a function is bijective, there is an inverse map. If a function's bijective, it means if you know the answer, if you know the output, where we ended up, then you can trace back and find the input. On the other hand, this map here is not bijective. So why is that? Well, if it's not bijective, it either means it's not injective, it's not surjective, or both. So this map here is not surjective because E is not paired with any element. It's not injective because D is paired with more than one element from the domain. So if a map is not injective or not surjective, it's not bijective, and it means the map does not have an inverse. All right, let's look at a map that we've already looked through in these lessons. So we're going to look again at Euler's totient function, which turns out to be a homomorphism. A homomorphism is a special type of map. So this notation means we call the map F, and it goes from set A to set B. A and B can be the same set. So a homomorphism satisfies this definition. F of x operation y is equal to f of x operation f of y. Here this operation can be whatever we want. Usually it's multiplication or addition. Now note, for the map to be a homomorphism, this has to be true for all elements in the first set in the domain. If there's just one or two elements in the domain for which this does not hold, then the map is not a homomorphism. So let's look again at Euler's totient function. We learned that this rule applies. Phi of mn equals phi of m times phi of n. So this satisfies the definition of a homomorphism. So phi is actually a map from the natural numbers to itself. Remember that what this does is it takes a natural number and it returns the number of integers less than the number that are co-prime to that number. So for example, phi of 7 is equal to 6 because there are 6 integers between and including 1 and 7 that are co-prime to 7. Of course, 1, 2, 3, 4, 5, 6 are all co-prime to 7. So we can see here that phi satisfies our definition for being a function. The significance of a function is that if you input one number, you only get one number. You only get one answer. So if you take some natural number, there's only one answer. There's only one possibility as to how many integers are co-prime to that number. So phi 7 equals 6. We only get one output, which is kind of what we want, particularly in things like computing. So it turns out if we take phi of 9, we also get 6 because there are 6 integers that are co-prime to 9, less than 9. So they are all the integers from 1 to 9 except 3, 6, and 9. So what we see here is that phi, the Euler's totient function, has actually mapped two different natural numbers to the same natural number. So that means straight away that this function cannot be injective. It is not one-to-one because there are elements that are mapped to by different elements in the domain. So is Euler's totient function surjective? What we're really asking here is it true that every single natural number is the answer to one of these, phi m? Does there exist an m such that phi m equals k for every k that is a natural number? And it turns out that the answer to that is no. Those numbers that are not mapped to are called non-totents. So the smallest example of this, or at least the smallest even example I know, is 14. There are many others other than 14, but 14 is a non-totient number. There is no natural number that has exactly 14 integers less than the number that are co-prime. So because this is a non-totient number, this is sufficient for us to say that not every natural number is the answer to one of these. Not every natural number is mapped to by Euler's totient function. So because it is neither injective nor surjective, it is not bijective. So bijective functions are good, as I said before, but we've seen an example here where if you know the answer, if you know the output of Euler's totient function, you can't map back to the original function. In other words, if I tell you that phi of k is equal to 6, you can't tell me what k is. You can't tell me what the input is. It could be 7 or 9. There could also be other integers, phi of k, that give you 6. So when it's not bijective, you can't trace back and find out where you started. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.